Okay, so last time we started to talk about the modular space of framed instantons. On R4, and I will pick a complex structure, then identify R4 with C2 of charge K, and I said that thanks to the work of famous people, this space is actually a quiver variety corresponding to a simplest quiver with one vertex and one loop, and more specifically, so it can be described in terms of the linear algebra data with two vector spaces n and k of dimensions little n and little k, and matrices B1, B2 acting in the space K, and matrix I sending n to k, and j sending k to n. So for the reasons which I'll delegate to the exercises, I will actually work with a slightly modified space. I'll call it the M bar, which is a partial, which is actually to get the instantons, you need to impose some. In addition to the equations which you impose on these matrices, and these are the equations. So they are denoted by letters mu because they have a meaning of moment maps for the action of the group UK. So in order to get instantons on R4, you need to solve these equations, mu c and mu r equal to 0. Select out of all solutions of these equations only those for which the quadruple B1, B2, I, and J has no stabilizer in the group UK, and then divide by the action of UK. So that's the modular space of instantons. Because you say that you delete some bad points, so those, namely those which have a stabilizer. For example, setting all matrices to 0 would certainly solve these equations, but that will, zero matrices have a maximal stabilizer, all of the group UK. So that produces a non-compact space. And since we want to integrate, we would like to get as close to the compact space as possible. And so in one approach, in the simplest approach to the compactification of the modular space of instantons, one simply relaxes this condition. So one takes all quadruples B1, B2, I, and J, solving these equations, divided by UK, and that produces something which is called the Uhlenbeck, in this case, partial compactification. If instead of R4 you worked on the compact form manifold, that would be actually compactification. Now, that would still produce a bad space for us, because obviously that space will have a scaling symmetry. So you can multiply all matrices by the same number. That preserves these equations. And so that the space which you will get by that procedure would have some kind of a conical structure. Yes? Yes, sorry. I don't like this equation anyway, so I sorry. All right. Okay, so there is this Uhlenbeck partial for R4, which consists of solving the equations mu c equals to 0, mu r equals to 0, and dividing by uk. So that gives a singular space so it has a conical singularity, and that's because of the scaling symmetry of these equations. So in order to avoid that, so one simple way to deal with scaling symmetry is to introduce a scale which breaks the scaling symmetry. And so that would, thank you. Thank you. And so smoothing out the tip of the cone is achieved by the Giesecke Nakajima partial compactification, and that's concretely means solving again the equation mu c equals to 0, but instead we set mu r equal not to 0 but to a scalar matrix. And so any non-zero r would do, but up to the obvious symmetries of these equations, you can assume that r is positive. And so that would create, so that would smooth out the tip of the cone, and in fact it would produce some topology. So the resulting space will have non-contractible cycles. Moreover, it will have some geometry, and so the cycles will have some characteristic size r. So if r is sent back to 0, then all these things collapse to a single point, and so we lose sight of this topology. So, so this partial compactification happens to be actually a modular space of something. For my purposes, I will, well, just to save time, I will not talk about what is it a modular space of. If you solve the exercises, you will get some idea of what this space parameterizes. For us, so what we need to do, we need to set up some integration theory. So we would like to set up the theory of integration over this space. Have I did what? Okay, so that's an exercise question. Have I imposed stability? So there is no. I gave you the definition. You take this all solutions of these equations and divide by the action of UK. Now the claim is that if R is positive, then that's any solution of these equations is stable in the sense that it has trivial stabilizer in this group. Now, for applications and for analysis, it is convenient to use an equivalent description. So that description, which involves solving equations with daggers, which is complicated, is equivalent to solving only mu c equals to 0 equation, imposing stability in algebraic geometry sense. So here stability means that, or in the sense of the representation theory of the quiver, it means that the image of I, so I applied to the space N, on which you act with all possible polynomials in B1, B2. In other words, you act with all possible paths of the quiver, giving these two loops. So generates all of the space K. So that's stability. In other words, there is no invariant subspace. There is no subspace in the space K which contains the image of I and is invariant under the action of B1 and B2. So there is no proper sub-representation of this quiver algebra. And so all this, now these conditions are invariant under the action of GLK. So I claim that these two descriptions are equivalent, and that's proven by the usual methods. Well, the way I like to think about it is to take the square of this equation, norm squared, and view it as a Morse Bott function on the space of matrices B1, B2, I, and J. Run the gradient flow. The gradient flow will actually be generated by a specific subgroup of GLK. So the flow keeps you within a given orbit of GLK action, and then this flow will bring you down to a critical point of the square of this function. And the critical point is either the absolute minimum, which is where you solve this equation, or if it is not a minimum, then you can prove that that will be the point where, which corresponds to a sub-representation of the quiver, proper sub-representation. That means that the stability condition is violated. And so that argument shows that there is one-to-one correspondence between the solutions of the right equations and the left conditions. Okay. So now we want to set up the integration theory over this moduli space, and we do it using the methods which I described. So we will not be solving these equations explicitly. That's too hard for most of the solutions. Instead, we will be integrating over the linear space of matrices, and then we'll introduce the multiplets chi and h for all these equations. We'll introduce the multiplets representing the symmetry UK, and we'll represent the multiplets representing the differential forms on the space of matrices. And so that gives us will give us a practical tool of evaluating integrals of some closed differential forms over this modular space in terms of the equivariant cohomology classes of the vector space of matrices. Now, the vector space being contractible, every equivariant cohomology class can be represented by an invariant polynomial on the Lie algebra of the group UK. And so the equivariant cohomology is simply just the invariant polynomials on the Lie algebra of the group UK, so UK invariant, which is the same thing as the SK symmetric functions polynomials in k variables. So these k variables are the virtual Chern roots of vector bundles with the structure group UK. So the way we learned how to compute these integrals, so of anything, is to, first try to interpret this integral as an integral over the ambient space in which my modular space, so it's the ambient space where where we're solving the equations and then dividing by the symmetry. So the ambient space here being the space of matrices. So the space of B1, B2, I, and J of some lift of differential form omega to the ambient space, and then multiplied by the form mu, which we discussed last time, and then times all the additional multiplets. Like sigma, sigma bar, eta, chi, h. All of these will enter. But now we need to recall that in order to be efficient in these calculations, in addition to the symmetry by which we divide, which is the group UK, it is useful to have a global symmetry, which you just keep as in your toolbox, but you don't divide by it. And that's what allows you to express this as a sum over fixed points of a global symmetry. So what is a global symmetry? So the global symmetry of my what are the symmetries of these equations, and what are the symmetries which act on the space of solutions of these equations modulo the group UK? Well, the one obvious symmetry is the one which looks at us. It's just the symmetry of changing the basis in the space N. So N here is a fixed space, so we can act. Okay, so let me just, so global symmetry UN. And so the element H of the group UN will act on my quadruple in this way. So remember, I acts from N to K, and J acts from K to N. So I can now multiply on the left and on the right. And we also have the symmetry which is inherited from the rotational symmetry of the space R4. Namely, we can do linear transformations of the matrices B1 and B2. And so there is also the group GL2. Well, there is a group. There is a group SU2 cross U1, which acts on the matrices B1 and B2 in a linear way. So the SU2 matrix alpha beta, beta bar, alpha bar would act on my matrices B1 and B2 in this linear fashion. Of course, if you don't pay attention to the second equation, if you only care about the equation mu c equals to 0, then any SL2 matrix will preserve it. So you don't need to, you could put alpha, beta, gamma, delta with determinant 1. But if I want to preserve the second equation, that imposes some additional constraints on this matrix, so it has to be an SU2 matrix. In addition, you can also multiply both matrices B1 and B2 by the same phase. So the phase will disappear from the second equation because you have B times B dagger. Now this equation will, the commutator will be multiplied by the square of that phase. And so in order to make this equation covariant, you also need to act on the matrices I and J. And there are some choices. So for my presentation today, I will make an asymmetric choice. So I will not touch the matrix I. Instead, I will multiply J by the square of the phase. And so that's a global symmetry. That's a symmetry which I'm going to use in order to efficiently compute my integrals of whatever, of whatever, of anything closed, which can be lifted to equivariant form. So the idea, as yesterday, is instead of solving, so if somebody hands you a differential form to integrate, you deform it, you promote it to the equivariant differential form, equivariant with respect to the global symmetry. And then you integrate that guy by fixed points, by fixed point formula. And then if you need, you can recover the answer to the original question by taking the limit when you send the equivariant parameters to 0. So the equivariant parameters I think I'm not sure it's mathematicians use these terms. It's a physical jargon, actually. So whenever mathematicians talk about equivariant cohomology of a point, which is the ordinary cohomology of the classifying space, which is again the algebra of symmetric. So these are W symmetric polynomials on the Cartan subalgebra of the corresponding Lie group G. So this is for compact Lie group. The arguments of these polynomials we physicists call equivariant parameters. So we call this. So this is called functions of equivariant parameters. And so this is justified by the interpretation of the equivariant forms as functions on the spec of the the functions of the on the Lie algebra varied in differential forms, which upon integration become conjugation invariant functions. So they're class functions on the Lie algebra, and therefore they're W invariant functions on the maximal torus. And so they are functions of equivariant parameters. So for the problem at hand, the equivariant parameters would be the coordinates on the Lie algebra of the maximal torus of Un. So this will be n complex numbers. So these are eigenvalues of a diagonal of a generic element in the Lie algebra of Un. And then the maximal torus of SU2 is one-dimensional. The maximal torus of U1 is one-dimensional. So the corresponding equivariant parameters for these groups will be called epsilon 1 plus epsilon 2 over 2 and epsilon 1 minus epsilon 2 over 2. So this strange notation becomes clear when you find out what these transformations generate when acting on the matrices B1 and B2. So infinitesimal transformation which they generate are epsilon 1 times B1, epsilon 2 times B2, 0, minus I times the diagonal matrix with eigenvalues A1 and N, and then A plus epsilon 1 plus epsilon 2, J. So this is the action of the global symmetry group on my variables. And now if we remember that we also have a local symmetry, local group, the group by which we divide, so the total, the local plus global transformation will involve, in addition to that, there will be a commutator of sigma with B1, there will be a commutator of sigma with B2, sigma times I minus j times sigma. So sigma here is the in the Lie algebra of UK. Thank you very much. So, in order to compute my covariant integrals, I need to find out what are the fixed points of the action of the global symmetry group on the moduli space. But then, if I lift, if I go from the modular space back to the ambient space on which my equations were defined, it means that I'm solving, I'm looking for the quadruples B1, B2, I, and J, which are fixed up to the action of the group we divide by. So the geometric picture is the following. So this is my ambient space. So this is the space of all matrices. And here are the orbits of the group GLK. Or if you like UK, it doesn't really matter for the argument. Now, the global symmetry group moves this points somehow. And so what we want the such points for which the motion actually happens to be along the orbit, so that on the modular space, which is the quotient, the point is truly fixed. So if my global transformation takes me away from the given orbit, it means that on the quotient space, my point is not fixed, it's moved. But if on the quotient space the point is fixed, it means that on the covering space, the point, if it moves along the orbit. In physics jargon, we say that the global symmetry transformation can be undone by a compensating local transformation. So for a given epsilon 1, epsilon 2, and A, you can find sigma such that this is equal to 0. 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 So finding fixed points means finding B1, B2, I, and J, preferably solving these equations, because we still want to impose these equations. Prefer obeying the stability condition, because that's what replaces solving this equation, which in addition admit such a sigma that this is all equal to 0. Now clearly, associating sigma to a choice of A, epsilon 1, epsilon 2 means that we now found a representation of the torus U1 to the n cross U1 squared into the group GLK, because sigma is an infinitesimal GLK transformation. So if I exponentiate and go from A, epsilon, and epsilon to the torus, the exponential of sigma will land me into the group GLK. And so it means that my space K is now a representation of this torus. So T becomes K becomes a T representation, and every representation of abelian group splits as a direct sum of the irreducible representations, which are one complex dimensional spaces. So my space K So K splits is a sum of what would be the good letter? So these are one-dimensional irreps of T. And each representation of T looks like, so it comes from a character. So on this one-dimensional space, the element of this torus acts by multiplication by a face, and this face has to be of the form e to the 2 pi square root of -1, some vector dot a plus some number n1 times n1 plus epsilon 1 plus some number n2 epsilon 2. So this is what the group elements so this is the element, this is a generic element of my group T, of my torus, and that's what it acts, that's how it acts in the space K sub gamma. So gamma corresponds to some choice of W and 1 and n2. So these are integers, and this is a vector, integral vector. So the question is to find this this integral data, and that's actually pretty easy. Well, first of all, right. Okay, so since we made the choice of a maximal torus of the group UN inside, so this choice of a torus corresponds to decomposition of the space N into the eigenspaces of this. So think of this as a group of diagonal matrices. So they're diagonal on some basis. That's the basis which I'm talking about. Now, so N alpha is generically just a one-dimensional space. Now let's act on this one-dimensional space with the operator I. That gives me a line, complex line. In K. And now the matrix, so we can now compute what does sigma, so sigma is an operator. Remember, sigma is an endomorphism of K. So I claim that this line is actually an eigenline for the operator sigma. So we use this equation. Sigma times I is equal to I times A. So this is equal to I times A times N alpha. And so N alpha is the eigenspace of A with the eigenvalue A alpha. Alpha equals 1 to N. So here A is a matrix, and here A sub alpha is a number. So that's what it means to be an eigenbasis, right? So these are eigenlines. It's not basis, it's a basis up to normalization. Eigenlines. So this is A sub alpha times A of N alpha. And so that actually already tells us that this line, it's an example of one of these irreps of the torus. And the corresponding vector W has components 0 everywhere except at the place alpha. So W here is 0, 0, 0, 1 at the place alpha, 0. Now, we can now act on the right. Sorry. Now the torus of this U1 cross U1 rotations, it doesn't act, it acts trivially on my operator I. And so the corresponding eigenvalues, so the corresponding weights n1 and n2 are equal to 0 for these vectors. n1 equals n2 equals to 0. Now, you can act on this eigenline by the operators b1 and b2. That way you generate a subspace. Let me call it K alpha. So this is what you get from these lines by acting with all possible polynomials on b1, b2. A priori, they are non-commuting polynomials, but it doesn't matter. So act in any order you like. So that way you generate some vector subspace, and the stability implies, so stability says that K sub alpha, the sum of K sub alpha is equal to K. And moreover, for generic A's, these spaces do not intersect. They actually, it's a direct sum. Because for the action of this torus, so all K alphas are eigenspaces of the n-dimensional torus with eigenvalue A sub alpha. Because A doesn't act on B1 and B2, so it sort of commutes trivially with B1 and B2. Sorry, what I yes. Okay, never mind. What we really want to find out is how the operator sigma acts on K alpha, and from these equations, from these relations. The relations being that the commutator of sigma would be 1 plus epsilon 1 b1 equals to 0. Commutators of sigma would be 2 plus epsilon 2 b2 equals to 0. It follows that if you act on this vector, and so it's an example of a vector you can get by acting with B matrices on this eigenline, on the line I of n alpha. By repeatedly using this equation, you will get immediately that this is the eigenvector, eigenline with the eigenvalue epsilon 1 times I minus 1 plus epsilon 2 times j minus 1 plus A sub alpha times this vector. So every vector of this form is an eigenvector if it is non-zero. It might be 0, so it might not actually correspond to any vector in K alpha. But if it is non-zero, it means that it gives you a non-trivial eigenvalue of the matrix sigma. Now, if you acted so because for different alphas, these eigenvalues contain different eigenvalues, so they're distinct. These spaces cannot intersect. So because if K alpha were to intersect with K beta, it would mean if it is non-empty, it means that there is some relation between the eigenvalues A alpha and A beta and epsilons. And as long as so I'm keeping my A's generic, which means I'm acting with the full n-dimensional torus. So so I do not allow that, and so then it follows from the fact that these eigenvalues are all distinct, that the spaces do not intersect. And now, it looks like you have effectively, you now have a situation where your space n splits as a sum of n one-dimensional spaces. And the space K splits as a sum of n subspaces for which you have the you have this structure. So it's a statement that you've heard at the lectures by Andre, that the fixed points of the framing torus on the quiver-variety is a product of the quiver-varieties for which the framing spaces are one-dimensional. And now, in our case, that leads to a serious simplification of these equations, because if n is one-dimensional, then it follows from these equations that the matrix J is equal to 0. And therefore, the matrices B1 and B2 commute. And therefore, this is all you can get. There is no, you gain nothing by permuting up matrices. So this is proven in the following simple way. Namely, you take the kernel of J, so J being the map from K to N, so its kernel is a subspace inside K, and I claim that this subspace contains the image of I, and it is B1 and B2 invariant. Well, it contains the image of I because if you take the trace of this equation, trace of mu c 0, because mu c is equal to 0. On the other hand, the trace of the commutator is 0, so this is a trace of I times j. But because of the cyclicity of the trace, this is the same thing as j times I. And the last step, in the last step, I used the fact that n is one-dimensional. So the trace of the scalar matrix is just the scalar itself. So once again, so ij is a square matrix of the size k by k, but j times I it's a matrix of the size n by n, which for one-dimensional n is just a scalar. Now this relation means that j annihilates the image of I, which is what I claim here. So that the image of I is in the kernel of j. And then if you now take the following identity, trace mu c of any expression of the form alpha b1 plus beta b2. Yes. Sorry, because it's the argument is kind of small, but it's yes. Okay, so I'm proving that for one-dimensional n, these equations and stability condition imply that j is equal to 0. So far I proved that the image of I is in the kernel of j, and now I want to prove that the kernel of j is so anything. So I want to prove that j acting on any polynomial of b1 and b2 is equal to 0. So for the moment, I want to prove the following, that if I take the so-called symmetrized product of matrices b1 and b2, which is what you get by taking some linear combination of alpha and beta, of b1 and b1 and b2 with complex coefficients, raise it to the power I, and act on with this on I, you get 0. So that we prove by computing the trace. So this is equal to the trace of mu c times alpha b1 plus beta b2 to the power L. Okay, so why is that? Well, mu c has two terms, I times j, and that's the left-hand side. And then there is a commutator. But the commutator of B1 with B2 times this guy is equal to 0 under the trace, because the commutator of B1 with B2 is up to a number, the commutator of B1 with this guy, alpha B1 plus beta B2. Okay, it's 1 over beta. And so what I have here is expression of the form trace, the commutator of two matrices times some matrix, this one of these matrices to the power L. Red is hard to see, but green is invisible. Okay. I think black is worse. Good idea. So you prefer green, right? Okay, is this visible enough? Do you see that? Well, you're the only one who has so you represent the people. Okay, good. That's why I'm asking you. So you're as a representative of people, can you see this identity? That the trace of a commutator x with y times x to the power L is equal to 0. Is it visible? Okay, thank you. All right. So where was I? Yes. So now, so from that, and then by a little argument with inductive argument, you show that any polynomial in B1 and B2 applied to I will be annihilated by J. Therefore, the kernel of J is the potentially destabilizing subspace, which by stability condition has to be all of the space K. And so the kernel of J is K, meaning that J is equal to 0. And so that gives finally, that gives a full description of the, well, it gives a description of the set of fixed points, namely the fixed points have the structure in which my space K splits as a sum of n subspaces, each subspace being organized as a Young diagram. So each square in the Young diagram is a one-dimensional subspace. It's so one of these K gammas. And the operators B1 act simply by shifting the squares in one position to the right or below. And if it moves you outside the Young diagram, it means that you get 0. And the uppermost corners of each Young diagram are the corresponding lines. So this is I of n1, this is I of n2, and this is I of n sub n. And the total size, so let me put it alpha here. So there is, so the Young diagram number alpha, so it's a set of pairs of integers. They're both greater than 1, and then they're bounded by the geometry of Young diagram, which are the members of the partition or the dual partition. So alpha runs between 1 and n. So these are my fixed points. So I described for you, so j is equal to 0. I maps the eigenlines in the n space to the upper left corners of the Young diagrams. And then the matrices B1 and B2 simply move these squares to the right or below until you move outside the Young diagram, which is when you get 0. And now the operator sigma, which is this compensating gauge transformation, which is needed for everything in my calculations, is a diagonal matrix in the basis given by the squares of Young diagrams, and its eigenvalue on the vector corresponding to the block ij in the diagram number alpha is given by this formula. So sigma is diagonal. So eigenvalues are a sub alpha plus epsilon 1 times I minus 1 plus epsilon 2 times j minus 1. Now, for all in all calculations which we are going to do, the character of the exponential of sigma, so trace of exponential of sigma in the space K pops up. So I will denote it, unfortunately for you, by the same letter K. So K stands for the vector space, but now I sort of replace it by its character. That's just, unfortunately, there's so many letters, so I have to optimize. And so this is, from this formula, this is the sum over alpha from 1 to n, e to the a sub alpha, and then the sum over I and j in the partition lambda alpha, q1 to the power I minus 1, q2 to the power j minus 1, where I denoted by q1 exponential of epsilon 1 and q2 exponential of epsilon 2. So this is something which we will be using a lot. Now the following structure will also show up, and this is what the origin of the so-called Y observable. It's the tautological. There is a tautological complex which you saw in Andrei's lectures. So namely, given the data, this ADHM data, we can set up the following sequence of spaces and maps. Let's call it D1 and D2. So D1 acts on kappa, sends it to, let's say, B2 kappa minus B1 kappa, J kappa, and D2 of kappa 1, kappa 2 psi is B1 kappa 1 plus B2 kappa 2 plus I times psi. Okay, maybe aesthetically it's better to write it in a different way. So let's call it B1 B2 and put here minus B2 plus B1. So the ADH, now the equation mu c equals to 0 is equivalent to the statement that this is a complex. So D2 composition with D1 is equal to 0. This is equivalent to mu c equals to 0, right? It's a simple exercise. So we can define, so we got ourselves a complex, and so we can compute its cohomology. So the cohomology potentially comes in 3 places. H0, which is the kernel of D1, H1, which is the kernel of D2 modular the image of D1, and H2, which is K modular the image of D2. So I claim that H2 is trivial thanks to stability. So okay, let me write it here. And so the homology of this complex can only be non-trivial in H0 or H1. So the way to prove this statement, you can do it algebraically. Let me do it again in the physics way. Suppose there is a vector in K which is not in the image of D2. So then it is using the Hermitian structure which I have. I can assume this vector is orthogonal. So suppose it's not 0. So then there exists vector psi in K, which is orthogonal to the image of D2. It means that psi dagger times B1 kappa 2 minus B2 kappa 1 plus I eta is equal to 0 for any kappa 1. Sorry for bad notation. So that was psi, and this is eta. So these are in K, this is in K, and this is in N. So it means that this vector eta is annihilated by B1 dagger, B2 dagger, and I dagger. So it is orthogonal to the image of I, and the subspace of such vectors is invariant under the action of B1 and B2. Therefore, by stability, eta is 0. Okay, so maybe right. So now I want to. So for my purposes, I need to compute the character of these cohomology groups. Again, the character of sigma. You see, what I forgot to say is that so sigma provides the representation of the torus of this torus of the global symmetry group in the space K. And this complex is actually T equivariant. So the cohomology groups will also be T representations. So it is useful to have the characters of these representations. More precisely, we will not need them separately, although we can do that separately, but we will need them the difference of these characters. So the trace of H1 minus trace of H0 minus trace of H2 for that matter, but we know this is 0 of e to the sigma. So that object will be called S. And by the usual Euler argument, this is the same thing as the alternating sum of the characters of the spaces of chains or cochains. So you don't really need to compute the cohomology because the exact and not so the things which are not in the kernel and things which are in the which are exact will drop out of this alternating sum. So this is equal to n. So n here being the trace over n of into the sigma, which is e to the a alpha. plus, now we need to, in computing this alternating sum, we need to, in order for this complex to be equivariant, I should have said that the spaces K, which enter different terms in this complex, have carry different representations of the torus T. So let's say this K is the same, is that K which we computed. Now, I'm acting with matrices B1 and B2, and B1 and B2 carry an additional weight of Q1 and Q2 respectively. So for this to be equivariant, I need to multiply this guy by Q1 and Q2. In other words, whatever character of T you had in the decomposition of K into irreducible components, you multiply that by an additional factor of Q1. And here multiplied by additional factor of Q2. And likewise here, since I'm now acting okay, I'm not doing this right. So actually, I need to twist it in the other direction. So there is something which is, I always get confused. So the characters and the dual. So B1 being multiplied by epsilon, it actually, so the arrow which it carries will actually be Q1 inverse. And so that would be the sending here. And this guy will carry Q2 inverse. So that will remove one character, one factor from here. And then further down here, we'll get the K without any additional twist. So with these remarks, we'll get Q1 plus Q2 times K minus Q1 Q2 K minus K, which can be simplified to n minus P1 2 K, where P is a notation which I'm going to use over and over. So P1 2 is 1 minus Q1, 1 minus Q2. So this is something which is called a virtual character. So this guy is a character. It's a sum of monomials in exponential of A and Q1 and Q2. Whereas here, I'm taking some alternating sum. So this is the expression of the form, the sum of plus minus the monomials in A alphas and some powers of Q1 and Q2. Now, this alternating sum is easy to compute because when you multiply K by factors like 1 minus Q1 or 1 minus Q2, since you see here you have some geometric series, this is some kind of a telescopic sum. So you get lots of cancellations. And when you carry these cancellations out, you get the following beautiful picture. So this is equal to the sum over alpha, e to the A alpha. And then this is the sum over the boxes in the outer boundary of the partition lambda alpha. And so that's what I will now introduce. So the upper boundary consists of all little squares which you can add to a Young diagram so that it still becomes a Young diagram. So there are squares which you can add at certain corners. The number of such corners depends on the Young diagram. So for some Young diagrams you have many corners. For some Young diagrams you have very few. So it's very non-universal. And so what you put here the content, the Q content, or exponential of the content of the corresponding square. So the content of the box with coordinates ij is epsilon 1 times I minus 1 plus epsilon 2 times j minus 1 minus q1, q2, the sum over the squares in the inner boundary of lambda alpha e to the content of that square. So the inner boundary is what you can remove. So these are the corners which I drew bold. So the number of inner corners is strictly one less than the number of the outer corners. And so for each alpha, you have the virtual character of rank 1. So there is exactly one term with a plus coefficient higher, more than the number of terms with minus coefficients. So now, from this virtual character, I can define now an observable, the thing which I want to study in my integrals over the modular space, which I call the y observable. And so this y observable is simply the Chern polynomial, in quote marks, of this topological complex. So the definition of y of x, so x is the auxiliary variable. So it's a product, it's a multiplicative version of that character of S. So it's a product, and here it's product over the squares in the outer boundary, product over the squares in the inner boundary. This is equal to the, so this is related to the, this S object by the so-called platistic exponent. So this is a platistic exponent of e to the x S star. How much time do I have? Do you know? 5 minutes? Okay. Very good. So okay, so now I can explain the notation. So now my notations are for any virtual character. So if you have a character which is a sum of plus minus exponents of something, so this something is always, it's a linear function in A, epsilon 1, epsilon 2. The platistic exponent is defined as a product. So it's a rational function where I put w with plus coefficients to denominator and w with minus to the numerator. So this is definition. So it's an operation which takes sums to products and now star, another operation. Okay, it's possible, yes. So Robo is right. So today I'm talking about cohomological calculations. In cohomology, that's what I need. I need the weights. When we talk about K-theory, we use a Q analog of that exponent, which is the product of this form. That's what you were talking about? And so this is literally the platistic exponent. So you take the character, so it's an exponent sum over n from 1 to infinity, 1 over n, you apply nth Adams separation to chi That's what you get. But, this is some limit of that. Remember, in localization formula, we need, in computing the ordinary integrals, we need the product of weights. And the weights are ultimately are what you see in exponents. So that's why we need this operation to in our formulas. So now in practical terms, yes, sorry, I started right definition and got distracted. So for that chi, the chi star is the same sum with plus minus, but then you change the sign of the weights. So we think of all these phases as all these exponents as phases. So we think of all weights as being purely imaginary, even though everything is complex analytic. But so the star operation just changes the sign. And in terms of the characters, it corresponds to taking a character of a dual space, dual representation. All right, so we are almost ready to do some calculation. So we need to, in addition to the tautological complex, there's of course also a tangent complex. And so we need to do things using fixed point formula. We need to figure out the way the tangent space to the fixed point so it's tangent space to the space mkn to the fixed point which corresponds to the collection of Young diagrams. Let me call it lambda under strike. So by the general arguments, this also has to be a representation of the torus. So what is it? So it's a C representation. What is its character? It is convenient to compute this character. It's convenient to realize that this tangent space is actually a cohomology of a complex, of a tangent complex. So the complex was described by Andre, but let me now, in more general setting, let me describe it quite explicitly. So tangent okay, so what do we have? We have our matrices B1, B2, I, and J. So looking at the tangent space means we try to, so if you have a solution to our equations, let's try to find a nearby solution to our equations. So we ask for the infinitesimal variations of our data. Now, these infinitesimal variations, they should obey the linearized equations. So the linearized equations being the commutator of B1 with delta B2 plus the commutator of B1, delta B1 with B2 plus delta I times J plus I times delta J should be equal to 0. And since we were looking at the solutions of these equations modular the action of the group GLK, infinitesimally, it means that we view some of these variations as trivial variations. So we identify the variations of the form the commutator of B1 with some psi, commutator of psi with B2 minus psi I J psi. So we view this as trivial. We view this as trivial. So what you see now, so I can call this object a differential. So the second differential applied to the variation delta B1, delta B2, delta I delta J. And I can call this the first differential applied to Xi. So what I see now again a three-term complex where I have endomorphisms of K. So this is where Xi sits, which are mapped by the map D1 into the two copies of endomorphisms of K, one for delta B1 and one for delta B2, plus Holmes of n to K, which is delta of I, plus Holmes K to n, that's delta J. And then by D2, this is mapped again to endomorphisms of K. And so my tangent space is actually the H1 of this complex. So this is my complex. And now, in very general situations, you have such complexes, and the cohomology in the 0 degree would correspond to infinitesimal automorphisms, and the cohomology in the second degree would correspond to the abstractions. So so you are in luck. You have an actual modular space at least to the second order if the only cohomology this complex has is the cohomology in the first term. And that's actually what we have in our case. So in our case, this is the only non-trivial cohomology. H0 is equal to 0. That means no stabilizer. And H2 is equals to 0 means no obstructions. And now using this complex, once we sit at a fixed point, now the space K is a representation of T, of the torus, N is a representation of the torus, everything is a representation of the torus. We can compute the character trace e to the sigma now acting in the tangent space. Well, what I really mean is that actually I want to compute the trace of the e to the a, q1, and q2, because that's the element of my torus T. So that's what this is whose character I'm computing actually. And so now by looking carefully at this sequence, you will conclude that this character is given by the following combination of things: n times k star plus q1, q2, n star k minus p1, 2, k times k star. And now, even though this looks like a virtual character, you can convince yourself that this is actually a pure character. Which reflects these facts, that h0 is equal to 0 and h2 equals to 0. I just defined star. So star means every exponent you see, you replace it by the negative exponent of a negative thing. Okay, so for Ezra, once again, so if chi is the sum of things like that, then chi star is the sum of e to the minus that. Okay. So in other words, it's a character of a dual representation. Moreover, you can actually, it's a nice exercise to not only to identify the individual weight subspaces, but actually identify the deformations. You can actually describe very explicitly what do the eigenspaces in this tangent space correspond to. But I leave it as an exercise, maybe. So, am I still in time, or I'm over time? Okay, very good. Very good. So now we are in the position to define the instanton partition function. So the partition function, so this is the partition function of some not very interesting theory. This is what we call pure Superman-Mills theory. Tomorrow we'll define more interesting things, but let's just as a warm-up. So this is going to be the sum over all topological charges. I have now a new parameter in the game called Q slash. So the parameter which counts the instantons. And then I do the integral over the modular space of instantons of charge K. And so this integral is T equivariant. Well, meaning, okay, so it's just an integral. So it's just an integral of the object we discussed. Namely, we take exponential, and then Q exact Q of the one form, which is obtained by taking the metric, T invariant metric on this modular space, and substituting here the vector field. Sorry, it's impossible to see. Okay, so it's lambda. So lambda, different lambda. Curly R. So curly R, it's a universally defined one form on M bar Kn. It's given by the contraction using the metric, T invariant metric, with the vector field, which is generated by some infinitesimal global transformation with parameters A star, epsilon 1 star, epsilon 2 star. So Q is the T equivariant de Rham differential. It depends on the parameters A, epsilon 1, epsilon 2. This R depends on some auxiliary parameters. But as long as these parameters are such that the integral converges, the integral does not depend on the value of these parameters. So as long as you choose anything for which the integral converges, you can then vary them. The answer will not change. So this partition function depends only on A, epsilon 1, epsilon 2, and Q. And by the arguments from yesterday, this is equal to the sum over the fixed points, which I described, which are the collections of Young diagrams. So it's a sum over all antiples of Young diagrams, Q to the sum of the sizes of these Young diagrams, one over the product of W's, where these W's are read off this formula. So this is the sum of W's, of exponential of W's. So it's maybe not very illuminating. Let me write it as so a product over some J. So J runs over some set of cardinality 2 and K, and the sums of exponents of Wj's are given by this formula. And finally, we can now use the observable which we defined to define the, we can now study expectation values of this observable. So not only the partition function, but we can also define some correlators. And for example, we can study the expectation values of the observable y of x, which will be now 1 over z, the sum over k from 0 to infinity, q to the k integral of m k n y inserted inside of the integral, y viewed as the cohomology class of the moduli space, again exponential qr, and this is equal to this 1 over z, the sum over all partitions, again the product 1 over the weights, and then times that product applied to the partitions lambda, this very partitions lambda. So it's a product over alpha, product over squares in the upper, in the outer boundary, divided by the product so this partition function, so now this expectation value, in addition to the parameters a, epsilon 1, epsilon 2, and q, depends also on the auxiliary variable x. And then each term in the expansion in q, as you can see, it's a rational function of x. So it's rational in x at fixed order in Q expansion. So the poles of this function of x are the interesting are very interesting because they reveal a certain hidden structure of this partition function, namely the different terms. So the terms of the of this sum are related to each other in an interesting way. So you see, this partition sum is organized in along the so-called Young graph. So you have the empty partition, and then you can add the box, and then you can add to it another box in this way or in that way, and then from that you can either go further down, or you can grow boxes in this way, and so on. And so each time you move further down in this graph, it's an infinite graph. And this is just for one alpha. We also have this for any alpha. So this is a product of n such graphs. So the terms in our expansion are the vertices in the product of n copies of this graph. Okay, and now this y function, its poles are the ways of going back in this picture. So for example, in the contribution of that Young diagram to the expectation value, the poles of y will be at x, which correspond to the contents of this box or of this box. And so if you look at the residue, so the point which I'm going to exploit tomorrow is that the residue at the pole corresponding to this box, so residue at this pole so the residue at this pole can be related to the expectation value of 1 over y coming from that partition. So the residue of y at this pole is related to the residue of that expression at the pole corresponding to the content of a square you can add to this point. Because 1 over y will have, so here I put y, you can also study 1 of the y in a similar way. Over z, sum of the lambdas, q lambda 1 plus lambda n, product 1 over wj. And now I take this expression but put it upside down. So product over alpha, product over delta square in the outer boundary, product over square in the lower boundary, inner boundary. And so we will tomorrow we will get some interesting combinations of y observable and 1 over y, maybe with shifted arguments, for which we'll get precise cancellation of the residues at the poles, and therefore the precise cancellation of the of poles, so that the expectation value of the whole expression will be not just a rational function; it will actually be a polynomial. It will have no poles, and from that we'll derive various interesting identities on Friday. Okay, I think that's enough for today. Yes, we'll do it either tomorrow or on Friday. So it will turn out that X is an object of the same nature as A. It also has a meaning of some framing equivariant parameter for some framing symmetry. But the modular space for which that will be a framing symmetry, we'll need to introduce. This will be the so-called modular space of crossed instantons. So we'll be crossing instantons on different spaces.